Okay. So the next talk will be just like we saw the previous talk. I mean, with the MPI, I mean, how do you really take or obtain good performance at the application and how you do co-design? So this is will be another presentation from performance and scalability of 3D FFT using heFFTe and MVAPICH. It will be presented by Natalie and Ahmed. So Natalie is a research assistant professor in the Innovative Computing Lab at the University of Tennessee, Knoxville. Her research interests include numerical methods for scientific computing and high-performance computing for scientific applications. Prior to ICL, she was a postdoc research associate in computational and applied mathematics at Rice University. She holds a PhD in theoretical and applied mechanics from the University of Illinois at Urbana-Champaign. Ahmed Abdel Fattah is a research assistant professor of the Innovative Computing Lab at the University of Tennessee. He received his PhD in computer science from KAUST in 2015, where he was a member of the ECRC. His research interests span HPC, parallel algorithms, general purpose GPU computing. He currently serves as the PI of the Magma library, some of you must be knowing. He has been acknowledged by NVIDIA and AMD for contributing to their numerical BLAST libraries, CU BLAST and ROC BLAST, respectively. So we have been actually working, the MVAPICH team, working with them and as well as Samir on an NSF-funded grant to really take the GPU, the runtime, the performance tools, and how it can help with the application. So, so we had the presentations from them last year, and they couldn't travel today. So let's see what are the very latest results. I believe, Natalie, you will be presenting. Ahmed, is he there? Or?
No, he had to go to an appointment today. So
yeah, he has an urgent appointment in a very important citizenship interview and all. So he has to, that is of highest priority than this. Okay. So Natalie, please share your slides and then get started. Yeah, we can see your slides. Yeah.
All right, great. Right, so I'm going to give the update this year for the work we've been doing as part of this joint NSF project with the MVAPICH team and the heFFTe library. So heFFTe has many team members over the years that have contributed. A lot of ETK, Miro did a lot of work. He's at Oak Ridge. And many people have moved on to various industry posts from our group, but their contributions remain. So I imagine most everyone at this meeting knows about the FFT, but it's an algorithm for computing a discrete Fourier transform, where we're going from real space to Fourier space. Or if we take the inverse, then that means, going backwards back to real space. And this discrete Fourier transform it's a memory bound operation, and the F part, the first F in FFT, the fast, is because the FFT algorithm reduces the n squared naive implementation down to an order n log n. So yeah, fast, but then even more memory bound. We have a lot of memory movement compared to compute time, especially on modern hardware where compute is so fast. And in heFFTe language, I guess this will be the forward and backward is the main call. You call forward, you do an FFT. You call backward, you do the inverse transform, but they're both kind of similar in terms of the demands on the system to get it done. And heFFTe came out of the DOE ECP exascale computing project. There were many large DOE applications that needed FFTs. FFT is especially used in molecular dynamics and like particle simulations and things like that. And so in order to get these applications ready to run on these exascale machines, large scale running on GPUs and everything, they needed an FFT library that could handle these machines as well. And so enter heFFTe. heFFTe has lots of different features to try to make things available to the different different users, whatever they may need. So there's different types of decompositions you can do, which I'm going to talk more about briefly. There's some reshaping options you can do. It can handle real and complex transforms. So you can do real to complex or even real to real. As we'll see, you can do the cosine or sine transforms and different precision options and things like that. There's different communication options. It's very flexible. And it's set up so that it has different backends. So it relies on these like single node FFT libraries. FFTW is a popular one for CPUs, or cuFFT for NVIDIA, rockFFT for AMD. And when you call from those libraries that are used in the different heFFTe backends, you only ever do a 1D FFT. So the way the algorithm works, you do 1D FFT and lots of communication and reshaping, transpose, etc. And so heFFTe handles all of that part and uses the 1D FFTs from whatever library the backends that it was built for. And you can switch between backends at runtime, so very convenient, write your code once and then run it different machines, different hardware. This diagram that we use a lot in heFFTe materials is demonstrating this pencil decomposition, which is a common decomposition type for FFTs, named because, as you can see, the communication pattern involves what looks like these pencils. But it can also do this slab decomposition, which would have a 2D slab instead of a simple pencil. And so when we have the slabs, then basically the strategy is for the communication part, maybe, you do fewer calls, fewer times that you're doing communication calls, but with more ranks involved in the call, like especially when you're doing the all-to-all, you think an all-to-all involving a bigger set of your total ranks. And so that, which strategy will work better will depend on, the size you're running at and things like that. So logically in FFT, these communications are all-to-all in terms of whatever group of ranks need to talk to each other, they all need to talk to each other. But the actual MPI calls used to accomplish that inside heFFTe can be different depending on the different communicator options. So heFFTe has two all-to-all communicator options, which of course use all-to-all or all-to-all-V in MPI. But there's also point-to-point options, as heFFTe calls it. So we have point-to-point, which uses send and I receive, and the pipelined point-to-point, which uses I send and I receive. And in general, the alt-all-V and the pipeline point-to-point tend to perform best on most of the machines that we've looked at least in recent years, more recent machines. But of course, all four options are available. And there's also this what's called a reordering option. And so what that does is reorder the data so that when you do those 1D FFT calls to the library, you have contiguous data and you don't need to make a strided call to the FFT library. Sometimes, we see that doesn't make too much of a difference in the benchmarks we run, but the option's there if you want to try it out and see if it works better for your use case. So the thing about heFFTe, I already mentioned, of course, that the FFT itself is very memory bound. And so when you go to these large scale multi-process, distributed FFTs, that is a very communication bound algorithm. So this is kind of looking at, this is a 16 ranks run on 4 nodes on a AMD MI300 GPU on the Tuolumne machine at Livermore. And this is doing one forward transform and then one backward transform, the dark gray part. And just looking at, where are we spending our time? And we see the blue part is the alt-all-V. It's, basically the whole thing. The FFT, 1D FFT is so fast compared to the other stuff going on that you can barely even see these tiny little yellow slivers, right? So basically, the communication's like the whole game. It's the most important part when we're running on these sort of machines. And that was with the pencil decomposition. This is now using the slab decomposition. And now we're doing the reordering. We weren't doing that before. And now this is for the point-to-point option. So instead of Alt-Al-V, we have send and I receive as our dark blue, and the light blue would be the MPI wait any. And again, we see pretty much communication or waiting on communication is where most of our time is spent. And if we go to the pipeline point to point, still the same thing. Now in heFFTe's tracing, this shows up always as wait time, but so yeah, we still see the actual scaling or doing 1D FFT so tiny we can barely see it. So what this means, is that the FFT is a good benchmarking vehicle for MPI implementations, because any improvement in the communication will have an immediate direct impact on the performance of heFFTe, because it's so critical to the actual performance of the distributed FFT. So that's what we've been doing in this project, is sort of using heFFTe as a vehicle to explore things with MVAPICH. And so an update from last year's talk, we have been looking recently at use of the compression option in MVAPICH to see if we can gain some speed while maintaining acceptable accuracy. We accept that we're going to lose some, of course, if we're doing lossy compression. But maybe that's okay in some uses. And also a little bit, we've looked at whether or not it would make sense to explore persistent communication options with FFT. And just in general, I have some new results on Tuolumne that we didn't show before because they're recent. So I'm going to start with the compression results. So these benchmarks were run on the Mare Nostrum 5 machine at the Barcelona Supercomputing Center. So there's 4 NVIDIA Hopper GPUs per node, and we're going to use 1 rank per GPU, so 4 ranks per node. And the standard heFFTe benchmarks that we usually run use random input data because, it's just for a benchmark. This isn't good, of course, for the lossy compression, which ZFP compression used, because ZFP assumes, obviously, to be useful, that there's some sort of smoothness or coherence in your data that you can exploit. So instead, we're just going and making a constant input into the benchmark, which does, some number of forward and backward transpose and then checks the final result. And we also used here the discrete cosine transform actually so that it's real to real instead of the standard FFT, because we also don't expect that the compression will work well with the complex data type, which is heFFTe's C++ library, it's the C++ data type. So real and imaginary parts are interleaved in the data. Right, so let's jump into the results. On the left here for these plots, we're going to have performance, so increasing number of nodes. And then on the right here, this is a plot of the final error after the benchmark is over. So this is with that slab decomposition and an all-to-all communicator, single precision. And we do see that, especially at this largest size, 32 nodes, which is 128 ranks, we get like 8% speed up using the compression, but actually don't, at this point, don't really have much error in the result. There is some error, extra digits of accuracy that were lost. These smaller number of nodes. So then this is like a strong scaling test. It's the same problem always, even as we increase the number of ranks. So that means, smaller number of nodes means bigger messages that need to get sent. And so we do see, several digits of accuracy loss as we expect with the lossy compression. But we still, this is still like 10 to the -3. So it's not like there's no accuracy left, right? Of course. And it is faster. This is similar results for if we use the pencil decomposition instead of the slabs. And if we go to double precision, now we have more options. So before we were using, so this uses the fixed bit width option in ZFP, and it was for 16 bits was the rate. And now we have two options. We have 32 and 16, because of course we can use 32 and still have it be compression when we have double precision, right? And so the blue part now in the middle is the using 32, and orange is still using 16. Of course, we can get more speed up, as you might expect, because now we're compressing more compared to the original data if we use the 16 rate, and still get a decent amount of accuracy at the end, even when using that rate. And if you need more accuracy, you can go to the higher 32-bit, and still it is a little faster for these as we get to larger number of nodes in particular. And with the pencils, you get even better performance improvement actually out of using the compression with the alt-all communicator, although you do see higher errors at kind of constant across all these different sizes that we're using. If we go to the point-to-point communication options, we see that there's no real benefit to using the compression. In fact, we lose performance often, which makes sense since we have the overhead now of doing the compression. And so there's not really, this is just one example, single precision and double precision for I chose pencils without no reordering, but it's, this is representative of all the point-to-point results, so I didn't put them all on the slide. So there's no real reason to use it if you're using the point-to-point communication. So kind of to wrap up this portion, there's definitely a potential for speed up if you can tolerate some loss of accuracy in your FFTs if you're using the all-to-all communication option in heFFTe. This question of complex numbers is definitely a limiting factor because we can't, even if we could expect in real data, a real user's data, not just the benchmark, even if we could expect some degree of smoothness or coherence within each component, real or imaginary, we can't obviously expect that there would be smoothness between the real and imaginary components if they're stored in this interleave format. So that is difficult for ZFP to really, be giving optimal performance. And I would say, the biggest users of heFFTe need the true Fourier transform. They're not using the cosine or sine transform. The molecular dynamics people and particle simulation people and all that. They're doing the full FFT. So if we aren't able to make it work for complex data, it would definitely limit the amount of applications that this would be potentially useful to. Right, so then moving on now to the next part, which is some new results on Tuolumne comparing MVAPICH 4.1 to what's currently, like as of right now, the default system MPI on the machine, which is MPICH 9.0.1. Again, we have 4 GPUs per node, so it corresponds nicely to Mare Nostrum in that way, and we'll use 1 rank per GPU, but now, of course, the GPU is the AMD MI300. This is with ROCm 6.4.2, and I'm always using the GPU-aware MPI for everything. So starting off with the some collectives all-to-all results for, this is the single precision with this slab decomposition, and we definitely see really good speed up for MVAPICH over MPICH in the all-to-all, both all-to-all and all-to-all V, especially this year, I mean 53% faster for 16 ranks. But even at these larger sizes, this is 256 ranks. It's very nice speed up for all-to-all V, and same thing for the pencils, even a little better actually in terms of how improvement over the system MPI. And similar story with double precision. again, we see, across the board, better performance from MVAPICH, and especially when we go to pencils for double precision, really, really good speed up, over twice as fast for this kind of smaller, moderate size, but still really nice speed up for the biggest size that we tested too. For the point-to-point options, again, this is just a representative plot. I didn't put all of them because I would say the takeaway is that the performance is kind of on par. Sometimes one is a little better, sometimes the other is a little better. There's no clear, winner or loser, but certainly, there's no penalty to using MVAPICH for point-to-point. And if you're doing collectives, the all-tall or all-tall-V, it'll be much faster. So it's still definitely, going to give you better performance on Tuolumne compared to the current default. And so finally, another thing that we had been looking at, which so far I've only tested out just a little bit on the Tuolumne machine, so not on a wide range of architectures, but we were interested in the idea of whether we should make persistent communication options available in heFFTe for users. So it seems like FFT applications would be a potential logical use case for it, that they would often have the case where you have one setup for your big FFT you're doing, and you're going to use the same communication patterns, the same grid for your FFT repeatedly throughout your simulation, but say just updating your data with time stepping, whatever. So we've implemented some experimental communicator options in heFFTe that do persistent all-to-all or point-to-point. And with my initial tests on this machine, with this hardware, it's, I would say, still very inconclusive with these versions of the libraries. For the MPitch, once I went to, so the default when we run these benchmarks is typically to do 5 runs of forward and backward transform. That's sort of like the default setting in heFFTe benchmarks. But if I go up to 20 runs after, then we could see some speed up in some cases. Mostly it was when I went to the largest size I tested, which was 64 nodes, and using the slab decomposition point to point, then you could see, potentially some decent size speed up once you go to 20 runs, which, getting better speed up at more runs is what you would expect with persistent, because the idea is you pay that cost for setting it up once, and then you can reuse it over and over again. So you would expect that the benefit would be greater if you could do more runs with the same configuration. But when I ran with the MVAPICH, it was the other way around. I actually got better speed up again, with point to point, and for the largest case I did, at 5 runs, but at 20, not as much. So it seems like maybe there's there might even be some noise in the data or something odd. I can't really explain this yet. And definitely so far kind of limited as far as, only very specific options really saw any benefit. And some of the other cases were even slower using the persistent compared to standard. So, not necessarily anything too striking at the moment, but again, the way that FFTs get used in application codes, it definitely seems like it could be an avenue for the future, something that might be useful to provide to heFFTe users. And so, just to kind of wrap everything up, heFFTe provides a natural sort of benchmark for MPI performance, since the communication portion is just so critical to its overall performance. And we've definitely seen some great results from MVAPICH on different machines compared to other MPI implementations for heFFTe. There's the potential to make use of the compression capabilities that MVAPICH has, with a question mark about, the best way to handle complex numbers. And, maybe, certainly from the heFFTe side, it's possible to implement using MPI persistent communication options. Whether or not this will be useful performance-wise in the future remains to be seen. So that's what I had. If anybody has questions, thank you.
Let's give thanks to Natalie. Any questions? Okay, so I just want to add a comment. I think she showed some of these errors when running MVAPICH with compression. So in fact, she reported first. So we have tried to resolve that in the latest release. So we are in touch with her, and we just didn't get time to install everything on those systems. So Natalie should be able to see now those error rates going down. Okay, so so that has been very helpful to see how to run the heFFTe with the latest MVAPICH on very large scale systems. Okay. Any questions from online? Okay. So if not, let's again, Natalie, thanks a lot for sharing your experience. So next we'll move to the talk here in person.